This webinar takes place within the framework of the Water Week of the Graduate School H2O Lyon, within the framework of the Global Water Day, which will take place on March 22nd. And there are several initiatives and events throughout the week, webinars or site visits, workshops, in order to discuss, learn, argue about water management. There is a QR code on the left-hand side where you can look at you can check the program and take advantage to tell you this morning we had the first webinar of the H2O Water Week, which had to do with the launching of an e-learning that will start on April 22nd, 25, by the way, and which will deal with the rivers and cities. Today's webinar discusses the large-scale pressures and impacts on river networks and associated ecosystems. And I will deliver a short introduction and talk about the objectives of the webinar, understanding that this webinar fits within a research project financed by the French National Research Council. The purpose of this is to address the impacts of urbanization on the floodplains social ecosystem on a global scale. So we'd like to have a sort of study situations throughout the world, highlight the impacts on the organization socials, and to propose tools as well, tools which could be used for research, but also tools to visualize and fuel the discussion at the global level about what is at stake associated with urbanization and possible solutions. This webinar fits within a series of webinars. We had one last year in 2024, where we prepared the stage, we set the stage, we talked about the objectives at the global level on the hydro systems with 4 speakers who kicked off the discussion on problems and solutions. Gérard Payen on governance at the global level of hydro systems. Jeff Opperman talking about the environmental challenges associated with floods. Victoria Q, who talked about the geopolitical challenges with the cooperative law, and of course myself, I delivered the project. The webinar today will deal more with the pressure and impacts on water and hydro systems, bearing in mind that the pressure and impacts at the global scale are different, vary from one region. You know, there could be overuse of resource, modification of flows and of sediment, of water, you know, degradation of habitats and pollution, of course, which could be scattered or local, the introduction of foreign or exotic non-vernacular species. So these interactions are multiple, they can be localized or scattered, and they take place at different scales, at all the scales of at the local scale, catchment basin or region. So if we want to look at some of the regions, we'll take, for example, the problem of damming and fragmentation, and so we now, you know, we now have a lot of knowledge at the global level, and we know that almost half of the rivers in the world, you know, are impacted by the presence of works, especially for their longitudinal flow. But this takes place on large dams, but we know that there are other works. You know, you see, for example, on the right side, the work which is focused more on hydropower plants, small hydropower plants, and we know they're all over the place, and we're still building them because there are needs as well. You know, so another example of pressure would be the overexploitation of resources, especially mining, for example, or sediments, in gravels or sand, and these pressures today are not studied at the global scale, but we can see their impact at the global scale thanks to satellite images, because their pressure they put on the systems and their impact are visible using images. You can see on the left-hand side the example of mining, bottom left, in the Rio Madre de Dios in Peru, and you can see the occurrence of extraction between the 90s and 2020, and we can see from the satellite. And you can see on the right-hand side other example of extraction of sediments in the rivers, the Sun River in India and the Maipo River in Chile, again, where we can see the impact of mining or sand extraction. Other pressures do exist. The pressure caused by climate change and the overuse of water resources, especially in dry zones, such as on the right top side, you can see in Phoenix, Arizona, you can see the reduction of water surfaces, before and after the years, or urbanization of alluvial plain. You can see bottom right, you can see spectacular example of this urban sprawl of the city of Lhasa in Tibet, which has, of course, a huge impact on the morphology of the river. We see, it used to be a braided river, and now it is a unique channel, so single channel. So what are also the impacts associated with such pressures? They're numerous, but one is very spectacular, which is the one associated with the loss of biodiversity, and with that, the loss of ecosystemic services. And studies are looking at this, which, and for aquatic ecosystem, it is much more faster than terrestrial ecosystems. There are impacts which are not known, but for example, in Europe, we know that more than half of all the water bodies have no longer achieved the good ecological quality according to the water framework, and the and we know that 40% of the water bodies have not reached the physical, chemical, or hydromorphological quality. So a lot of those pressures, and we know that a lot of those pressures are not known. And the graphic on the right-hand side shows you the gray part, which tells you the amount of information missing to be able to assess such effects. Now, following this introduction, let me introduce the program of the webinar, which I'm animating with Hervé Piéguet, and Stu. We go learn more about the pressures and the impact at the global scale on ecosystem. We'll talk the pressures, the impacts, and to do this, there will be 4 presentations coming from colleagues. Well, we do have with us Michel Thieme from WWF in the US, then Mathis Kondolf from the Berkeley University, Colorado, Mathis Messager from Lyon, from the INRAE Riverly Lab, and Fanny Bourgeau from the ANS Lyon. And without further ado, I will give the floor to Michel. I'll turn off my screen, and Michel, you are on.
Good morning, good afternoon, good evening, everyone. I'm Michelle Thieme from World Wildlife Fund, and I'm really happy to be here and have the opportunity to share with you today about global freshwater biodiversity, taking a very whirlwind tour of the current status and threats, and also talking a little bit about solutions, and look forward to the discussion and debate and hearing more from each of you. So just a quick overview of my outline here. I'm going to start with looking at freshwater biodiversity status, then I'll quickly move to the causes of decline. See, my video is off also, oddly. There we go. Here I am. And then I'll end by talking or sharing a bit about what can be done to stop and reverse the decline in freshwater biodiversity. So, as you all know, freshwaters are full of life. This is just a representative picture of some of the multiple taxa that occur within freshwaters. Life is often out of sight and so out of view of the public, and I think in many ways it is very undervalued because of that. It's also true that freshwater ecosystems represent just a tiny proportion of the surface of the Earth. Estimates are around 1 to 2% of the Earth's surface is covered by freshwater ecosystems. And this really tiny proportion of the Earth's surface hosts an abundance of life. It is home to at least 12% of all known or described species, 1/3 of described vertebrate species, and incredibly, over half of all described fish species. So the oceans are so vast, covering over 70% of the Earth, but the freshwaters in this tiny proportion host more than half of all freshwater or all fish species, and new species are being described every year, about 200 species per year. That being said, unfortunately, we are in a biodiversity crisis, and we're seeing vertebrate populations decline on average for those that are monitored by about 73% since 1970. What is driving that? Unfortunately, it is freshwater species populations. So that the decline in freshwater species populations has been measured to be about 85%. Of course, we know that this is only a small proportion of species that are monitored, and it's just the vertebrate populations. But we see that other assessments similarly show high levels of decline or threat to freshwater species, such as this recent study that came out from Sayer et al. In early 2025 in Nature, which shows that about a quarter of freshwater fauna are threatened with extinction. This study only looked at decapods, freshwater fishes, and odonates. And you can see that there's a little bit of a difference depending on which taxa you're looking at, with decapods having the highest level of threat, around 30%. Okay, I'm going to move now to what is causing the decline. Barbara already touched on many of these themes, so they will be familiar. But this diagram I love because it very succinctly shows the complexity of inland water ecosystem integrity and the 5 major components of the health of freshwater systems. Obviously, all of these are interconnected, but it helps sometimes to chunk them out. And we see that there are threats that are acting on each of these components of the integrity of freshwater systems. For the hydrologic regime, changes in flows caused by over-abstraction, basin water transfers, dams, urbanization. For water quality, we see a whole variety of point and non-point sources of toxic chemicals, nutrients, and other chemicals that change the health of freshwater systems. For connectivity, there's fragmentation, of course, by dams and other infrastructure, but there's also artificial connectivity where we're reconnecting systems that were never connected before by basin transfers or removing natural barriers. Invasive species and non-natives plus overharvesting affect the biotic composition of these waters. And of course, for physical habitat, it's the direct conversion of wetlands and other habitats, as well as degradation of those habitats in stream and in the water bodies. Overlaying all of this, we know climate change is the shark in our future, and water is its teeth. And we are seeing this with increased and more severe floods, droughts, and extreme heat events that are affecting people and nature all around the world. And we see this with increased frequency. So, which threats and their magnitude, how they're affecting biodiversity really varies inland water body by inland water body. You can't generalize about that. But here are a few examples of the picture that we see at the global level that gives a snapshot of some of the impacts on freshwater systems. So for both hydrologic regime and water quality, we have surpassed the planetary boundary for freshwater use and for nitrogen and phosphorus use, which are affecting both of those components of ecosystem health. For connectivity, 2/3 of long rivers, those over 500 kilometers in length, are fragmented or they've lost connectivity in one of the 4 important components of river connectivity and are considered no longer free-flowing. About 55% of basins globally host non-native species. And at least, and the statistics here vary wildly depending on which study you go to, but I will say at least 20% of wetlands have been lost globally since 1700. So what can we say about these threats? Which are most dominant and impacting species the most? That is very difficult to know and at a global scale. And there are lots of studies that are trying to pinpoint and tease out which of these threats are dominant. We can say that certain habitats have more threatened species. This again is from the Sayer et al. 2025 Nature paper that was recently published. We see, for example, that permanent rivers really have the highest, by far, proportion of threatened freshwater species with them compared to other habitat types. We also see that there are certain threats that affect multiple species multiple times. And from that study, we also know that 84% of all threatened species have more than one threat. So we can say that threats rarely operate in isolation in freshwater systems. And again, a recent study from Spiller et al. Evaluated 45 IUCN threats across a wider number of species, 38,000 freshwater species, and found that about 64% of all threat pairs are connected globally. There's still a lot that's unknown about how these threats work, whether they're synergistic or antagonistic in certain places, and how they interact with each other. But we can say that globally there is co-occurrence of threats to freshwater species. So what can be done to stop and reverse the decline of freshwater biodiversity? There are several recent developments on the policy landscape that offer some hope. First is the agreement and ratification of the Kunming-Montreal Global Biodiversity Framework under the Convention on Biological Diversity. Throughout the targets in this framework, inland waters shows up in a way that it has never shown up before. So just pull out a few example targets here. Targets 2 and 3 both aim to have at least 30% of inland waters either restored under Target 2 or protected or conserved under Target 3 by 2030. And Target 11 focuses on nature-based solutions for ecosystems and ecosystem services, and it has a big focus on inland waters as well. One other thing I want to say about this is that the framework is very clear on highlighting the importance and forward-leaning, putting Indigenous and traditional territories and Indigenous peoples and local communities' rights at the forefront. And that is really important in the context of inland waters and its conservation, because the lives and livelihoods of these communities are so intertwined with the health of freshwater systems. Another positive recent development is the Freshwater Challenge. This is a country-driven initiative that aims to bring 300,000 kilometers of degraded rivers and 350 million hectares of degraded wetlands under restoration by 2030, and to conserve intact freshwater ecosystems. There are 50 countries that have signed up or joined the Freshwater Challenge, and there's a lot of interest and momentum to implement the ambitious targets that have been set and that are connected, honestly, to the Convention on Biological Diversity and many other conventions and commitments that countries already have in place, but really calling out the importance of inland waters and targets around those. In the scientific space, there was a publication in 2020 led by a colleague of mine on the Freshwater Biodiversity Emergency Recovery Plan. And this lays out really what needs to be done in the freshwater conservation space if we want to see a change in the trajectory for freshwater species. And it lays out 6 main actions along that trajectory of what needs to happen. Of course, it's easy to lay out at a high level these actions that need to be implemented, but doing so and really understanding and unpacking that takes another look. And the authors recognized that and also went ahead and had a compendium of 6 different papers that go a lot deeper on each of these issues. And I led one of those, which focused on actions to restore and maintain freshwater connectivity. This is a figure from that paper that highlights a few of the main actions that we recommended, everything from intervening at the policy level around planning, as well as looking at actions like fish passage, dam operations, dam removal, floodplain reconnection, and protections for rivers and other freshwater systems to safeguard connectivity early before development happens. Given the interest and focus of this group on floodplains, I'm going to end with 2 examples of actions that can be taken that are focused on floodplains that can and do have real impact for freshwater biodiversity. The first is an example that you may be familiar with from the Yolo bypass in California. I love this photo. It's a photo taken in 2017 that shows high river flows in California and the bypass in full flood stage. So the bypass was put in place many, many decades ago with an intent of carrying 80% of the flood flows during major flows of the Sacramento River in order to avoid flooding of the city of Sacramento and important infrastructure in that part of the state. It happens that this intervention has really important and high biodiversity co-benefits. So it's key habitat for waterfowl that are migrating through the Pacific Flyway. 42 species of fish also use the floodplain, including spawning and rearing habitat for a federally listed cyprinid and for young Chinook salmon. The second project that I'll highlight is one that's proposed. It's not yet in place, but some colleagues of mine who are working in the Mekong Basin have outlined a proposal of what might be possible with restoration of the Gut Ting marsh along the Mekong River in Thailand. And the actions that are needed in this case are to reconnect the marsh to the main stem of the river to reconnect the flood flows of water, but also the important sediment flows, as well as removal of invasive species within the marsh itself. And we would expect, they've done some calculations of what is possible in terms of benefits, and could expect upwards of $80,000 of revenue per year for local communities from increased fisheries production and tourism for seeing water birds along the river. And with that, I will end, and thank you very much for your attention. I put my contact information on the slide, and happy to take any questions. Back over to you, Barbara.
Thank you very much, Michelle. Thank you for your presentation. Great arguments, very solid, and some which opens to possible solutions and points of action. Yet we know the threats are very worrying. So time is time for question. We got 5 minutes for question. So I can see a first question. Emmanuel Mignot.
Yes, I see the question. Thank you. Thanks very much. Yes, that is the case. So there have been several studies that show that channelization and levees and dikes on the river and limiting inundation of the floodplain cause upstream flooding. And so it has implications for cities that are located upstream of floodplains that are getting channelized and with levees and dikes put in. I'm sure there are specialists on this call who know a lot more about this than I, so I also welcome others to put answers in the chat. But I certainly am aware of several studies that have been published that show this to be the case. Thank you, Emmanuel. Apologies, I missed the question. Yes, so definitely I think whenever you change the natural habitat, and we see this actually in some of the benefits from the cases that I just highlighted where you reconnect the floodplain, that the habitats for especially freshwater fish and wetland birds in terms of nursery areas, rearing, spawning, feeding areas are limited by that change and loss of the floodplain habitat. So it certainly affects many inland water dependent species when you change that natural flooding regime.
Another question about the participation of inhabitants to the project, the local population. How do you involve the local population to such projects?
Yeah, thanks very much for this question. It depends a lot on the particular project. So like in California, there's a lot of government involvement and processes that are part of the state regulations and how they introduce new changes or changes in the flood regime and so on with the local communities and get stakeholder feedback and buy-in. In parts of the developing world, there's less of a regulatory structure that already lays that out, but the involvement of local communities is often done by groups like WWF and others, where we have relationships with local NGOs and organize stakeholder meetings to get feedback on proposed changes and ideas for changing the flood regime or restoring habitat. And of course, what's really important with that is making sure that you hear any concerns and also that there's funding available to support local communities in terms of alternative livelihoods if they are dependent on certain aspects that will be affected by those changes.
Thank you. Do we have other questions or not? Or maybe one, Mathis, you have one.
Moi, j'ai une
Mathis,
petite question.
I do have a question.
Thank you, Michel. Let me just turn off the transcription. I didn't remember the existence of the freshwater challenge, and I imagine that it overlaps with other previous commitments by nations like the COM in Montreal, Biodiversity Framework, or the Sustainable Development Goals. And what I'm wondering is, from your view, to which extent do these commitments really trigger new actions on the ground, or are these ways to use actions that are already planned on the ground to tick boxes to get them recognized? Because these commitments are kind of multiplied, and I'm wondering how much do these really drive change?
Yeah, thank you for that question, Mathis. Great question. So I should have clarified this. The Freshwater Challenge is not a new global convention framework. It's really meant to be a way to catalyze countries to raise up inland waters in their existing commitments. So no commitment there is anything additional to what countries have already committed to under CBD, under UNCCD, or others. It's really just a way to highlight, because often what we find is that countries haven't recognized the role of freshwater systems in delivering against their existing commitments. So this is a way to help support the funneling of funding to countries to support actions that are focused on inland waters. And we've seen interest, for example, the GEF recently announced at the UNCCD that they were going to fund $5 million towards the Freshwater Challenge commitments, which is really the commitments under all these other conventions. So that's just to say that's just a start. We're really hoping that this will mobilize a lot more and incentivize countries to raise up the value of freshwater systems in their existing commitments.
Great, thank you. That's much clearer.
Merci beaucoup. Merci, Michel, pour cette présentation.
Thank you, Michel, for your presentation and the discussion. We move on now to the second presentation. Kondolf, you talk about the Mekong River. So we'll now focus on this catchment of this basin, international river basin, which is submitted to high pressures because of dams being built. Matt, are you back?
All right. Welcome, everyone, and thanks for the introduction, INRAE. Michel's talk set up mine very well. Unfortunately, the Mekong is an example of many of the multiple simultaneous stressors that Michel was describing, and it's a river that had biodiversity second only to the Amazon, but unfortunately, we can see unfolding before us many changes that are not for the best of the ecosystem. Let's start by looking at the Mekong Basin itself. It's quite a large basin. It encompasses the upper reaches are in China, has a little bit of the basin in Burma, and quite a bit in Thailand, Laos, Cambodia, and Vietnam. It has a relatively high discharge and very strong seasonal differences in flow, and the ecosystem is adapted to these seasonal changes. Remarkably, the fisheries support about 60 million people. At least this has been the case. Fisheries are declining precipitously now, but this is really an extraordinary human ecosystem that to have this kind of support for people depending on proteins from the river. And if we look at the Mekong Delta, that is an economic hotspot. Over 17 million people live there. The Delta is an engine for the economy of Vietnam and the region as a whole, and it produces 7% of the rice traded internationally. It's a very small area. It's about the size of the Netherlands, and yet it has this huge global importance economically. Yet it is threatened, as we will talk about more next. Let's see. Moving on. Now, talking about dams and water connection, fish, I want to talk a little bit about sediment, which is sometimes overlooked. And it was certainly overlooked when you look at some of the early reports of making plans to build dams in the Mekong. You don't see any mention of sediment basically in these reports. But sediment is essential to maintain channel form, to build beaches and deltas along the coast. And borrowing a concept that Stan Shum introduced in the 60s, we can consider the mountainous headwaters as a zone of erosion, supplying the system with most of its sediment. And then the middle reaches of the rivers are primarily zones of transport. They're moving the sediment from high to low. And then at the coast or some other base level, you have deposition. And so here's where you see your deltas and your beaches. And they are dependent on the sediment that's carried down from the whole basin. When we build dams across a river, we cut off the sediment supply. Depending on the size of the dams, we may still be allowing finer sediment to pass, but certainly all the coarser sediment, the sands and the gravels, are trapped behind the dam. Yet the dams will still release water. The water still has energy to move sediment, but the sediment load has been taken away. So this leads to what we call hungry water. And this excess energy typically results in channel incision or downcutting and channel widening. And the starvation of sediment is often compounded by mining of sand and gravel from channels. You know, I just realized I didn't click on the right. Okay, much better. Sorry about that. So here's an example. This bridge that's undermined here in the photo, that is a result of mining sand and gravel in a river reach downstream of a dam. So the dams cut off the supply of coarse sediment, and then mechanically excavating the gravel from the riverbed has created further incision or downcutting, which propagates up and downstream from the mine site and results in this undercutting of the bridge. That bridge had been built 15 years before this photo was taken. So the Department of Transportation in California had to replace this bridge after 15 years, which is not what they want to do. So again, looking at the Mekong, a key thing to understand about this system is that historically, naturally, it was sediment rich. Something like 140 to 160 million tons per year were transported downstream. And many of the functions of the river depend on sediment. Nutrients, which are carried with the fine-grained sediment, the productivity of the Tonle Sap wetlands, the fertility of the floodplain, and maintenance of the delta itself. A lot of the sediment, about half of it, was coming from the upper Mekong in China. That only contributed 20% of the flow, but it was contributing 50% of the sediment. It is now, as we'll see, pretty much thoroughly dammed. In this upper reach in China, also called the Lansang, there's been a lot of development in recent decades, and it's pretty well documented that some of the road construction has increased sediment yields tenfold in certain areas. And so you think, well, this would produce more sediment that would come downstream in the river, but it's all trapped in dams. So the net effect, the net change in sediment coming from the upper basin has been a decrease because of the dams. Now, looking at the unique biophysical system of the Mekong, Um, Here we see this dynamic interplay of tectonics and hydrology, creating a really unique system. Sediment and nutrients are carried by the annual flood pulse. They support very high productivity. Here we're looking at a map. I need to explain this because it's not obvious if you're not familiar with the geography. This is the Mekong River main stem flowing like here. What happened? Let me go back. So here's the Mekong flowing down like this. And this is a tributary, the Tonle Sap River, okay, which comes in right at the Cambodian capital, Phnom Penh. And in the headwaters of the Tonle Sap is this large lake called Tonle Sap Lake. So this is a tectonically formed basin, a large basin, relatively shallow. What happens when the Mekong is in its annual flood, when the flows can be easily 20 times what they are in the lower flow parts of the year? The Mekong River is so high that it drives reverse flow up the Tonle Sap River into Tonle Sap Lake. The lake expands from the dark blue area to the light blue area. It expands over 4 times, or historically it had. The annual fluctuations are being reduced now by dams, but this is the way the system works. So there's this huge area of shallowly inundated floodplain, which, as Michelle was mentioning, these kind of habitats are tremendously productive. And so on this shallowly inundated floodplain, juvenile fish are having a feeding frenzy. It's a big buffet. And as they get larger, and then when the main stem Mekong drops and this lake begins to drain, a lot of these fish are carried downstream with the draining water. And then you have set up what's called the dye fishery, all these rafts with these nets that are catching fish on their way out. And this is tremendously important for the human economy in this region. There are more than 850 fish species identified. As I mentioned, second highest biodiversity after the Amazon. Also, floodplain agriculture, very important. And historically, that's been supported by nutrient-rich silts deposited in floods. Unfortunately, because a lot of these silts are now being trapped by dams upstream, this natural fertilizer is not occurring, so farmers are turning more and more to chemical fertilizers. The ecological importance of the river is well documented, and I would just say that in some cases the role of sediment probably needs to be more explicitly acknowledged. Turning now to the delta downstream, as I mentioned, 17 million people living here, very intensive agricultural production, also a lot of light industry and other kinds of economic activities. But this feature is, how should I say, delicate. It's fragile. It's a relatively flat, low-lying landform. It averages less than 1 meter above sea level, about 40,000 square kilometers here. And it's a young feature. If you go back 7,000 years ago, the coastline was located at Phnom Penh. Everything that we know as the Delta today, this whole landform, was built out by deposition of sediment over the last 7,000 years. And here you see where the coastline was 5,000 years ago, 4,500 years ago, 3,000 to 2,000 years ago. Looking at this line here, when the pyramids were built, this is where the coast of the Mekong Delta was that time. Well, this has been a steady progradation or increase of the surface area of the Delta over these last millennia. But now the coastline is retreating. It's starting to erode, subside, and the coast is retreating. And why? it's because of a lack of sediment supply to maintain the coastal features. You always have wave erosion, so you have to be bringing in new sediment to compensate for that, and accelerated subsidence, as we'll look at. So when we look at the threats to the natural function of the Mekong River and its floodplains and its delta, we see reduction in sediment supply from dams, which I'll specify in a moment. And that has immediate and long-term effects. This is why I say a slow-moving disaster, because the most serious impacts will be more evident later on. You have some immediate effect on wash load, or the suspended sediment, the silt and clay and nutrients that are carried in the water. Some of that is trapped in these dams, especially the big ones upstream in China. But some of that gets through. What is always trapped is the sand and the gravel, and this, of course, is essential, especially the sand for maintaining the beaches in the delta. We have a more immediate effect from reducing sediment supply from sand mining. And then you also have dikes that prevent sediment from going out and depositing on the delta surface. Groundwater pumping is causing subsidence. And of course, on top of that, we have the accelerated sea level rise that is experienced globally. So looking at the effects of dams, these are the dams that have been built early on in the Lansang, the upper reach of the river in China. And they've cut off supply, what was 50% of the river sediment supply is cut off. And then we have all these dams that are under construction or planned or built in the lower Mekong, Laos, Cambodia, and Vietnam. 130 dams are on the table, 11 of those on the main stem, of which 3 have been built. So this is a lot of dams, and they're all going to be trapping sediment. Now, do they have to trap sediment? Well, that's a good question, and the Mekong River Commission published main stem dam guidelines. And actually in those dam guidelines, you see a requirement that the dam developers implement measures to sustainably manage sediment. There's even an expression of making the dam invisible to sediment. And how would you do that? You do that through what's called sluicing of sediment at high flow, where you open up a gate and you allow the floodwaters to move through the reservoir at a high velocity and carry the sediment through. Or you have a bypass, where you allow the sediment to take a shortcut to downstream reaches carrying its sediment, but not bringing that into the reservoir where it would deposit. Okay, so back to this question of long-term, short-term. Long-term, the dams will trap sediment that's needed by the delta. We conducted an analysis, and it's pretty clear that if all these dams are built as planned, looking at their individual trap efficiencies and accumulating those over the whole basin, that there will be only 4% of the natural sediment load of the river reaching the delta. In the long run, the delta simply cannot survive without its sediment load. That's why it's there, because of its sediment. If you take that away, the delta goes away. That will take some time, though, because there's a lag in the time in which sand would move down through the system to the delta. But if you cut it off, and some years later you see the effect. More immediately, the effect of sand mining, which has been very intense in channels in the delta and in Cambodia just upstream. There's a huge demand for construction aggregates, sand and gravel, domestically and globally. If you go to the Alibaba website, you can find Mekong polished colored pebblestone for sale for $90 a ton. And there have been tremendous exports to Singapore. According to the UN, you can see the sand exports on the order of 70 million metric tons, 70 million tons by 2015. Other important drivers affecting the delta, the distributaries through the delta have been channelized, and this means that the sand is directed immediately out to sea. It cannot deposit on the delta plain. Subsidence, of course, there's the eustatic or global subsidence or sea level rise, but this is exacerbated by the land actually sinking as a result of freshwater pumping. And this is actually the thing that is driving the loss of the delta most quickly at the moment. And again, our recent topography shows that the average elevation of the delta is only 0.82 meters, which is not very high. Now, these existential threats to the delta have not really been acknowledged in policy. The Mekong Delta Master Plan cites flooding, salinity, and coastal erosion as problems, but it doesn't recognize them as symptoms of these larger underlying problems, the subsidence, the lack of sediment supply. So the plan proposes engineering fixes to the symptoms, but my concern is that these will not be sustainable in the long run. The report talks about subsidence rates, but it doesn't extrapolate into the future. And a similar problem with World Bank documents. There's been about $2 billion spent on development projects in the Delta. And these, reports are great, but they don't acknowledge the existential threat. So our concern is really we need to confront this existential threat, and we need some changes in policy that would allow the Delta to continue into the future. That would include avoiding high impact dams that would trap a lot of sediment, where we can retrofit dams to pass sediment through them or around them. Phase out riverbed sand mining. This is going to be a hard one to swallow, but in fact, we are just about to run out of sand that can be extracted. And then there's some changes that need to be done in agriculture to the Delta that would allow the sand carried in these distributaries to spread out in the Delta and deposit instead of being shot out into the ocean directly without any chance to deposit. With the current business as usual, what's going on now, we would expect 90% of the Delta to be under the sea by 2100. With a change in management, our model suggests that we could get it down to maybe only 10% submerged. In the long term, with continued sea level rise, the Delta is probably going to be gone, but at least we could prolong its life a bit. And in the theme of Michelle's talk, recognizing the tremendous biodiversity importance of the Mekong system. So there are social and economic reasons that we would want to maintain the Delta, but it's part of the whole river system. And understanding that, we should not be making our choices strictly on short-term profit. We should be thinking long-term benefit to people and the ecosystem.
Thank you very much, Matt, for this brilliant presentation. Very well documented, illustrated, which explains the scope of the problem of this case study. It is quite spectacular, actually. Now, do we have questions from the participants on this topic? Otherwise, in the meantime, I might have a question. So, Matt, you mentioned a difference of understanding between what goes on within the Delta, people who live in the Delta, the population in the Delta, and those who are upstream, especially with the sediment management plan, indication for better management of dams and sediment management. But now, could we make sure that there would be discussion, there would be converging views from the Delta and from the sediment managers, if in a way?
Yeah. Well, you need some platform in which discussions can occur. And the Mekong River Commission has been around since the 60s. And it is the logical platform in which you would have these discussions. But it does not include China. And China has chosen not to be a participant. Meantime, in the last several years, China has created its own sort of version of Mekong River Commission and is getting some participation from the other countries. But that's a big problem. But even within the lower basin countries, so Cambodia, Thailand, Laos, and Vietnam, it's difficult for them to agree. There were some important agreements, and one of those having to do with sediment was that these dams that were going to be built along the main stem should incorporate some of the sediment management features. But there's no requirement that they do this. All the countries pledge that they will consult with the Mekong River Commission and the other countries, but the other countries can say, and the commission can say, well, please do this, and of course the country building the dam, they can choose to do it or not. So there's maybe a carrot, but there's not really a stick involved.
Yeah. There is another question, but I guess it's in the same line. You have already replied to this. It was about if it exists any agreement for the management of water and the sediment. So, but I think you replied to that. And so there is another question that is about are there big commercial lobbying interested at play?
Yes, of course. The sand mining is certainly one of them, although it's a good question. To what degree is it dominated by large companies versus smaller? Because you do see a lot of small companies all over the place mining sand. But yes, there are big commercial interests, and certainly some of the agriculture that's being developed now is really at an industrial scale. So we're seeing commercial interests of different kinds playing out in this space.
Thank you. There is a question for Mathis, and then we switch. On the ground, are people that depend on tonal saps fisheries or was town are on the delta realizing the existential threats? Are you aware of social mobilization?
Okay, yeah. So are the people in the towns depend on tonally sap fisheries aware? They are aware to the extent that fish yields and fish catches have been declining. So I think there is certainly an awareness at that level. Whether I don't think the existential threat to the delta, however, is understood. It must be understood by some of the technical specialists involved in these World Bank development projects, things like this. But it's a bit like coming out and saying that the emperor has no clothes. I think there's a lot of reluctance for people to emphasize that point, even though to me it would be the first step in getting people motivated enough to do something, because certainly stopping or reducing any of these practices, such as sand mining, will be politically very, very challenging.
Thank you, Matt. Other questions are likely to come, but we have to keep on going with our presentations. So thank you again for this excellent, very elegant presentation. Striking example. So now I will give the floor to Mathis Messager, who will talk about another challenge at the global scale.
Thank you everybody for being here. So today I'm going to talk about what non-perennial rivers and streams are, how prevalent they are globally, how they are commonly excluded from environmental regulation, and whether rivers are increasingly drying. But before I really start, I would like you to take 5 seconds just to picture a river or stream. What is your token river image? And my guess is that it didn't really look like this. And this is the Albertine River. It's about 50 kilometers from Lyon. And what we see here is a natural phenomenon. This river dries several months a year, often naturally. And it probably didn't look like this either. This is a small stream in Kenya. But you're not the only one, because whether scientists or managers usually, historically and until recently, have tended to overlook non-perennial rivers and really focus the study and management of rivers on those that flow year-round. Even though these that stop flowing are really prevalent, not only in arid and semi-arid regions, but also in more wet climates like France or even Brazil, for example. And this is an example of a river, the Calavon River in southern France. And here you see it really high flows in autumn after heavy rains. Here it is at base flow, mostly fed by groundwater during winter. And once late spring, early summer come about, the river stops flowing and it starts being disconnected into pools. And this is autumn again, but at late summer, the channel can really fully dry out. And the reason we care about these ecosystems, these social ecosystems, is that they support unique aquatic species that are adapted to these dynamic cycles of wetting and drying. And most importantly, at the network scale, they support high biodiversity because of a dynamic mosaic of habitats, of flowing pools and dry habitats. They're also hotspots of biogeochemical activity for carbon, for example, during the rewetting events, and provide ecosystem services that are specific to the wet and dry phases, including cultural significance. But how really globally prevalent are they? Until recently wasn't well recognized, because we estimated them based on assuming that they occur only in arid areas or semi-arid areas, based on subsets of the globe or based on hypothesis. And for example, previous estimates had it at between 29 to 30%, 36%, sorry, of the global river network being non-perennial. But more recently, as part of my PhD thesis, we developed a model to estimate that of all mapped rivers and streams by length, 41% would stop to flow at least 1 day per year on average. And we were constrained in this initial model to only those that are over 100 liters per second or 0.1 cubic meters per second due to data constraints. And this, the Schwalbach in Frankfurt is an example of these. And here you can see it's around probably 50 liters per second during summer, to give you a sense of what we mean. But when we extrapolated this model down to 0.01 cubic meters per second to really account for those headwaters and smaller streams, we estimated that 60% of all of the river network length on Earth stopped to flow at least 1 day per year. And what this really means is that flow intermittence is not really an exception, it's really the rule across the river network on Earth, and that it really occurs across all continents and climates. Now, it's worth highlighting this because despite the prevalence, these type of rivers have been undervalued, understudied, and under-monitored. And this has led to the exclusion from protective regulations and mismanagement, which eventually caused and is causing still the degradation. They are subject to very much the same stressors and impacts as other rivers, but on top of it, for example, the bed when dry are often degraded or polluted. And because they're in such a delicate balance hydrologically, excessive water withdrawals can really worsen the effects that long periods of drying can have on these ecosystems. And they're also, because there's so little water, they can be easily polluted. And one of the presumed reasons for the ongoing degradation of non-perennial rivers is that they're often excluded from protective laws. And in France, for example, one of the cornerstones of environmental policy is the water law, the Loi sur l'eau, which regulates all installations and activities on or near watercourses that may pose risks to public health and safety, impede the free flow of water, diminish the water resource, increase the risk of flooding, or seriously harm the quality or diversity of the aquatic environment. And what this law implies is that whoever plans one of these activities must either declare what they will do or request an authorization. And for example, if you're going to withdraw more than 1,000 cubic meters per year or significantly alter flow, that takes an authorization. But not all water bodies qualify under this law. In fact, they must meet 3 cumulative criteria. The first is that they must have a clearly defined channel of natural origin, even if it was subsequently modified. The second is that they must be fed by a spring. And the third is that they must have sufficient flow most of the year. And that's the legal language. It says that flow can be intermittent, but it must be sufficient considering local conditions. And as you can imagine, this leaves a lot of gray area for interpretation when applying this law. And luckily in France, we have in the past 10 years made maps of what counts and doesn't count. So in 2023, I compiled and harmonized the maps of watercourses for all departments by contacting every administrative area in France. And here you can see the resulting map with, in blue, the hydrographic segments that were present in topographic maps previously and that have been deemed to qualify as a watercourse under the water law. In red, you can see non-watercourses, so those that did not meet those criteria or were thought to not meet those criteria. And in green, those that remain to be classified. And you can see already that there are sometimes drastic differences across departments, which highlights this part of interpretation of this definition. And coming back to non-perennial rivers, what we found is that those hydrographic segments that were estimated to be intermittent on topographic maps made up 59% of the mapped network length. But of those that were considered to be non-watercourses, they comprised 81%, which means that intermittent rivers were overrepresented by 37%. And this was really variable as well between departments. And several of them, for example, intermittent rivers in red there, for example, were overrepresented by over 50%, which really highlights how these types of systems tend to be excluded from regulation, and this make the impacts of them on them more invisible because we have no trace, no documentation of requests for authorization, for example. And I focused on France because there is no other country where a study like this has been done using actual data, regulatory maps. But we've looked at laws, the definitions of watercourses across the world, and found that they were actually quite commonly excluded for being too intermittent. So that includes the Clean Water Act in the US, the Water Act of Australia and or South Africa, which are all descendants of common legal heritages. But we also see in other countries like Colombia, etc. In the US, for example, the only other country where a model was trained to predict whether a watercourse could be protected under the Clean Water Act. Here you can see in brown those that are considered to be unlikely to be protected, and those in green those considered to be likely. You can see how in the US Southwest, this is the arid part of the country, you have the most excluded watercourses. And this was before 2020, and since then, actually, it's been I don't even know how to qualify how bad this looks, but this doesn't just affect now intermittent rivers, obviously. And this is not just at the country level. It's also at the global level and global agreement level. For the Sustainable Development Goals, for example, here is a map that is a model predicting the amount of water as a percentage of total runoff, total discharge in a year that should be kept in the river to conserve the ecosystem. The environmental flow is a percentage of mean annual runoff. And this model, you can see, excludes most areas in semi-arid and arid climates because it's considered at the time that there was no legitimacy to establish environmental flow for these systems. The issue is that it is used to calculate water stress and to go towards the targets of the Sustainable Development Goal number 6 on water. And so far, I've mostly talked about naturally non-perennial rivers, but really a big question is, are rivers increasingly drying? Will there be many more human-induced non-perennial rivers? And the short answer is yes, surely, but we still don't know how much. And we don't even have estimates of how much, but we're working on it. And the last global model that exists dates back from 2012, Doll and Schmidt, and it modeled flow regime shifts from perennial to non-perennial and vice versa between broadly the 70s and the 2050s due to climate change. And it found that these flow regimes shift on about 6 to 7% of land area and going both ways about equally. So 3.5% more or less should go from perennial to non-perennial and vice versa. The issue with these models is that they're really coarse. Here you see the pixels are 50 kilometers wide, so they don't take into account what's going on upstream in the smaller rivers and streams. And they are really, just like climate change model, they tend to focus more on the average trends rather than low flows and extremes. So they're not so reliable. And Petra et al. Will not mind if I say that because we're now working together on trying to improve this. And here's, for example, a model that's under review, where we try to go really at the river reach scale to predict what will happen in terms of flow intermittence across Europe. And this map shows the changes in the percentage of months where which undergo intermittence stops to flow. So the change between the 2000s, more or less, climate normal, and the 2080s climate normal. And this is an upper level scenario, so more of a worst case scenario. And what we find is that what we find is that 17% of reaches experienced at least one non-perennial month between 1985 and 2014, but that 2.8% of total reaches in Europe would switch from perennial to non-perennial. That seems little, but actually represents almost 90,000 kilometers of rivers that would switch. And 0.7% would switch the other way. And for those that are already non-perennial, we predict that a lot of them would actually have many more months of drying. But this is not the case everywhere. And the reason why I say there are many unknowns is that we know of places that are going to become wetter and that have already become wetter. And this is the case, for example, of the Arctic, where Feng et al. In 2021 modeled, including with satellite imagery, the annual average number of zero flow days, so of drying days, for all intermittent reaches across the Arctic. And what they found is that from 1984 to 2020, actually, this number of zero flow days decreased on average. So drying was less often and shorter. So there are lots of unknowns, and actually one of the big unknowns is exactly how humans will adapt or how they will worsen the situation with their water uses. Because in a drier climate, often with also no CO2 in the atmosphere, the effect of climate change will very much depend on whether we will keep the same crops and irrigate even more to make up for these changes. So this has not yet been modeled comprehensively or robustly yet. And you may ask, okay, I started the presentation by saying drying is great for biodiversity. There are biogeochemical activity in ecosystem services, but is it so bad that rivers are drying? And as Michel was saying, is that when we change an ecosystem, this creates a transition into something else that, from our point of view, may be better or worse. But in this case, species have been adapted to these cycles of drying and rewetting. And shifting to a cycle from perennial to non-perennial is predicted to mostly cause an abrupt decrease in biodiversity initially, and maybe, hopefully, a recovery. And this picture, for example, is from the Murray-Darling Basin in Australia during the millennium drought, where fish kills, where the entire fish population of the river would die because of hypoxia, the lack of oxygen, was a common sight. And this kind of event often accompanies or precedes drying. And surprisingly, we know actually quite little about what are the effects on ecosystems and how they may recover when we switch from perennial to non-perennial or vice versa. So this is why I don't have data to show very much, but hopefully we will know more. So my take-home messages for you in this is that most rivers and streams are non-perennial, that flow intermittence is a natural phenomenon in many places, including in what we think of wet climates. These natural non-perennial rivers are ecologically, economically, and culturally important, but they are undervalued, under-monitored, and underprotected. And we predict that rivers are going to increasingly dry globally, and in most of the places we know, but there's still a lot of unknowns, and they're not necessarily go dry everywhere at the same time. It might be a lot more extreme driven, like with droughts. And finally, anthropogenic and natural drying are not to be conflated, but we also have a lot of unknowns on this side, and we still need to dig into it. So thank you to GloUrb for organizing this for you to be here, and H2 Lyon as well, who partly funded my thesis. Thank you.
Thank you, Mathis, for this presentation, which is a good illustration of what is at stake and the understanding of intermittent rivers and everything what is at stake in this when there is this extension at the global level. So we got a Q&A session. We got about 3 minutes left. Your first question coming from Leo.
How would you improve the general definition of rivers to acknowledge intermittent rivers in water laws? Tu le vois dans le chat?
Yes, thank you. This is actually a really interesting question because last week we were interviewed at the National Assembly on this very question. In our case, we think that the law currently is so vague that it could be interpreted more inclusively to say that taking into account that non-perennial rivers are common across climates, they can be included, and so that wouldn't go against the law to include them a lot more. But to us, what we try to highlight is that it's not really, this hydrological criterion does not make sense even functionally of what a river is and what a river network is, because a river network is interconnected. What happens upstream, whether it flows 2 weeks a year or 3 months a year, will impact what's going downstream. So before its revision, the Clean Water Act in the US considered that a water body was qualified for the law when it had a significant nexus with other waters. That is, it was connected and significantly impacted the rest of the river network. And to us, that is the main criterion of what qualifies as something that needs to be protected. If you impact it, does it impact the rest of the system?
Thank you. Do we have any other questions? Thank you. I do have a question, possibly on the extension of intermittence. In your opinion, you talked about the impact of climate change, but there are several other anthropic drivers. In your opinion, which are the regions which are most impacted or most vulnerable? J'entends pas.
Pardon. Can you hear now?
Yeah. Okay.
Okay. Sorry. Our main water consumption is often agriculture. So I think that the places where we're at risk of running our water resources into the ground are those where the mismatch between the crops we're growing and the climate we're going to have is going to grow. And so this gap in water demand is likely to be the most impactful. And that's the case in France, for example. I think we're going to see that in many areas of France. And if we put a lot of our consumption on groundwater, because surface water will not be able to provide as much, then this is also going to impact the base flow, which will cause intermittence to worsen. So we may think of switching to groundwater when we lack surface water, but this will have feedback effects. But geographically, we need to model it.
Thank you, Mathis. We move on now to the next presentation. To add to this notion of integrity, in your various presentations, you did insist on several threats. Michel did introduce this notion of complex of threats. For you, what would be the means of action that could be employed to overcome that? Do we have to go through more stringent regulation or in the countries? Are there countries which are leading in that domain to take into account the threats or to overcome the threats? I mean, is there a reflection or a global approach, for example, for a global approach? Does it exist? Are you aware of it?
I'm going to go on a little flex on this. And I will take France, for example, as an example that we know well. Because in France, what's curious is that we have ambitious objectives. We have laws also that we can leverage, strong laws that we can leverage to improve the conditions of the rivers. But we do struggle with implementing some of those laws, even though they exist. And so it's already, there are some places that have a really good legal framework. It's not being put into action, and when it doesn't have teeth, and the teeth are not being used. And I think that's kind of a way I'm trying to approach my science with also communication is trying to show the ecosystem services provided by healthy rivers so that there is a willingness to actually conserve the integrity of these river ecosystems, because it's river ecosystems that have integrity that provide a diversity of ecosystem services. Because if we manage a river very narrowly for one objective, we tend to get rid of many of these co-benefits. And I think there is a really tough communication work, let's say, in some ways, and quantitative demonstration of these services that are provided to society by healthy ecosystems. And I think that's a big step, because in France, for example, if we're going to apply those water restrictions, for example, which are hard and require sacrifices on the part of some stakeholders, we need to demonstrate that there will be co-benefits to these restrictions. I think we're not there yet. We say that there are co-benefits, but we're still struggling to quantify some of them.
Thank you, Mathis. Thank you to all the speakers for this fueling this discussion, for sharing your knowledge, and for being very strict with the clock. Very professional. Thank you all. Thank you, Pierre, Claire-Lise, and your team, the HR. Thank you that's me. Okay. And we'll meet again probably next year for another seminar in line with this of this one and the one of last year. But this time we'll try to have practitioners and to work on beyond the threats we have identified today, the set of threats, well, to identify potential solutions or to evidence great examples that exist throughout the world, which show how we deal with this issue and we fight for Earth. Thank you all. Have a great day and see you soon.